All right. Well, chapter 3 is the chapter on stoichiometry. And stoichiometry is just the part of chemistry where we do measuring. We count how much stuff we have. Often, chapter 3 is the part of chemistry where a lot of people realize that they don't like doing chemistry because of the math. However, I'm going to walk you through this very systematically, and hopefully, after doing this, you will be quite comfortable with doing the math in chemistry. All right, so let's start by talking about the law of conservation of mass. And this is a law, an observation really that is found to be true, is really all the law is, made by Antoine Lavoisier, a famous French scientist. He was an aristocrat here. He even has a painting by the famous artist David. And by the way, if you ever find yourself at the Metropolitan Museum of Art in New York City, then I am going to recommend you go find this piece of art. It is a marvelous work of art. It's very large. I think it's about 8 feet tall. And you can't miss it if you walk into the hall where this particular piece of art is. But I like it because it shows some of his equipment. But on to the law of conservation of mass. What the law of conservation of mass tells us is that when we're doing chemical reactions, we're going to have an equal amount of matter both before and after the experiment. That is in essence what the law of conservation of mass. Now, he said it in French, of course, because he was French. But that is the law of conservation of mass. Now, this is not an entirely obvious thing. And the reason for this is, well, let's say you didn't know the law of conservation of mass was a thing, and you didn't have a modern way of thinking about things. Well, you might look at a chemical reaction like burning a piece of wood. You burn the piece of wood, and let's say the wood starts off and it's 1 kilogram. Well, after you burn the wood, you may only have, 50 grams of ash that is left over. And you may think, well, where did the rest of that mass go? Well, as modern people, we know that what happens is that a lot of the substances in there get converted into carbon dioxide and water and numerous other gases, but those gases, that's what makes all the difference. Well, the big thing that was different that Lavoisier did is that he would take the piece of wood and he would put it into a chamber, but he would trap all of the gases. And so he was able to determine that indeed, even when it seems like maybe you're not having the same amount of mass before and after, in fact, it is an equal amount of mass. It's just that some of them become gases. So anyway, that's an important concept and one of the building blocks for what we're going to be doing here. So our next thing that we're going to look at is chemical equations. And chemical equations are just a simple way of representing chemical reactions. The chemical reaction that we're going to look at first is the combustion of methane. So if we take methane, for every molecule of methane, we'll use up 2 molecules of oxygen, we'll produce 1 molecule of carbon dioxide, and 2 molecules of water. Now, I've got a video here, and you can click on this video and watch it. I've already clicked on it and got it set up, but you can watch this at home if you wish. All right, and so here, this is a video of some people who are professors at the University of Alaska in Fairbanks. And if you're familiar, of course, with Fairbanks, it's quite cold up there a big chunk of the year. And the lakes up there will freeze over and be frozen solid for many months in a row. And so many lakes, including this one, produce some natural gas. The natural gas is mostly made up of methane. And that methane, when it's released in the summer, it just bubbles up to the top, and and it just goes into the atmosphere. However, during the winter, it builds up under the ice, and so sometimes people like to catch it on fire. So here I'm going to play this video.
Oh my God! Your spirit? Spirit? On the side, yeah. Right there. Whoa!
All right, so clearly that's very exciting. The methane catches on fire, and it is released into the atmosphere, and then, of course, combines with the oxygen and burns. It's very exciting. All right, so that is the chemical reaction of methane. I like to show the picture so everybody's clear on exactly what's going on there. Well, we want to represent this in a very concise manner. And rather than draw out the molecules every time we do this, because that is just not very efficient, we like to use chemical formulas and put them together in chemical equations. So the way that chemical equations work is that we will put reactants over on the left side of the equation. And so these are the chemicals that we started with. Methane and oxygen was in the air. The arrow indicates that these chemicals will proceed to make these chemicals. And so the products are over on the right side of the equation. And so that is how we represent them. Now, I want to look at a couple of the other components here, and that is the states and the coefficients. So the states of the reactants and the products appear in parentheses. And of course, G stands for gas. If we had a solid, we'd use the letter S. For liquid, we use the letter L. And for things that are in aqueous solution, which is a water solution, we use the letters AQ. But you'll see all of these are gas in this particular reaction. The other thing are the coefficients. The coefficients, they balance the number of atoms. So the coefficients here, this 2 in front of oxygen, means that there are 2 molecules of oxygen. Of course, that means something different than the numbers that are the subscripts. The subscripts tell us how many of each atom are in each molecule. So if we wanted to figure out how many oxygen atoms are used in this reaction, it's 2 times 2, so 4 of them. All right, so you want to, of course, be familiar with that. We're going to balance some of these equations here in just a few minutes. So let's look at how it is that we balance chemical equations. The very first step in balancing a chemical equation is that we have to have the correct chemical formulas. If you start off with the wrong chemical formulas, you will get the wrong answer. So you always have to start with the correct chemical formulas. So that's always, always, always the first step. Now, sometimes I will give you the correct chemical formulas, and sometimes I will just give you a word description of a particular chemical reaction. And you'll have to come up with the correct chemical formulas based on what you learned in Chapter 2. So you'll have to be patient as you do this, because it takes a little bit of effort, a little bit of patience to do this. So always use the correct chemical formulas. Here I've got another combustion reaction. This is the reaction between ethane, which is related to methane. It's a similar compound. It just has an extra carbon in it. It burns in oxygen, also producing carbon dioxide and water. So when we look at that, that is our correct chemical formulas. So next, what we want to do is we need to ask ourselves, is this equation balanced? Do we have the same number of each type of atom on both sides? Remember, in Dalton's atomic theory, we are required to have the same number of each atom on each side. And if we look here, this one definitely is not balanced. We've got 2 carbons on the left and only 1 carbon on the right. We've got 6 hydrogens on the left and 2 hydrogens on the right. We've got 2 oxygens on the left and 3 oxygens on the right. So nothing here is balanced. So no, this equation is not balanced. All right, well, let's figure out how to balance it. So we're going to balance it one element at a time. And before we do this, I will say that there's more than one way to balance equations. I would say there's three general ways to do this. One is to just randomly change the coefficients until you come up with one that works. And that is not a very effective method. That's kind of like going to the grocery store without a list and you're hungry and you're not sure what meals you're going to make. It's a dangerous thing to do, and you often will make mistakes or bad decisions. So a second way is to use a system of linear equations, which is a little bit more complicated than the method we're going to use. The system of linear equations, though, is quite effective. A third way of doing it, which is the way I'm going to recommend, is to balance one element at a time and then go to the next element and then to the next element. And to do this, we'll need to put coefficients in front of each chemical. And then once we put them there, they're locked in place. In this case, I'm going to recommend picking an element that is in one substance on each side of the equation. So here you'll notice that we've got carbon is only in one substance on the left, and ethane, and it's only in one substance on the right. So carbon is a good choice. We could also pick hydrogen. Hydrogen is only in ethane on the left, and over on the right, it is only in water. Of course, oxygen, you'll see oxygen is in two different things on the product side of the equation. So we're going to avoid oxygen in this particular situation. So we'll avoid oxygen. Now, when I have two choices like carbon and hydrogen here, I usually pick the bigger one, the one with the larger atomic number. Carbon has an atomic number of 6. If you look at your periodic table, you'll see it has an atomic number of 6, whereas oxygen has an atomic number of 1. So I'm going to pick carbon because it's bigger. All right, so we'll try carbon to start with. Okay, well, next thing that we want to do, so the next thing that we want to do is I'm going to remind you of this. Don't change a coefficient more than once until the end. So once you put a coefficient in front of something, you can't change it unless you've changed all the other coefficients that you've already placed. So we're going to start here with carbon. You'll notice we've got 2 carbons, so I'm going to lock those 2 carbons in place by putting a 1 in front of ethane here. So now we've locked those 2 carbons in place. To balance the carbon, we will now put a 2 in front of carbon dioxide. So now we've got 2 carbons on each side of the equation. Carbon is balanced. Next, we're going to go to the other element that we could have picked. Remember, we picked carbon because it was bigger, but now we're going to pick hydrogen. So we look over here, there are 6 hydrogens in ethane, and with 6 hydrogens in ethane and water over here has 2, we're going to put a 3 in front of the water, and that balances the hydrogens. All we have left is oxygen, and you'll see that over on the right side, what we have locked in place already, 2 times 2 is 4, plus 3 more gives us a total of 7. So we have 7 oxygens on the right, and we need to get 7 oxygens out of this O2. Well, obviously, O2, that's an even number of oxygens. So if we multiply it by a whole number, we're going to get an even number. We need a fractional number here. And so you can put 3.5 or 3.5, or I like to put it as an improper fraction. And that makes it easy because we know we needed 7. Well, we can just put 7 halves here. So 7 halves. Now, the reason we can leave that as an improper fraction is that we typically will go through and balance this. We'll typically go through and balance this to get rid of any fractions. And of course, once we've placed all of these coefficients, it should be balanced, but we're going to get rid of fractions. And so we just need to multiply all of the coefficients by some number that will get rid of this fraction and make it a whole number. Well, since it's 7 halves, it's really easy to see. We just need to multiply by 2. So we're going to multiply the entire equation through by 2 to eliminate that fraction. So when we multiply that through by 2, we'll get this. So 2 times 1 is 2, 2 times 7 halves is 7, 2 times 2 is 4, and 2 times 3 is 6. Now, we're not quite done, and this last step is important, and I want you to do this. Double check the math to make sure you haven't made a mistake. I have been doing this for decades, and sometimes I still make a mistake, particularly if I'm doing shortcuts and not being systematic about it. So let's double check it. And the way I recommend checking it is just start with the elements and work your way from left to right. So we're going to start with carbon. 2 times 2 is 4. 4 times 1 is 4. Carbon is balanced. Hydrogen, 2 times 6 is 12. 6 times 2, also 12. So hydrogen is balanced. 7 times 2 is 14. 4 times 2 is 8. 6 times 1 is 6. 8 plus 6 is also 14. So that is balanced. All right, so we now want to look at problem 3.12. So I'm going to switch over to my document camera here. And we're going to be looking at balancing these equations. And we'll just be systematic about it, just like what we were doing. All right, so here we've got lithium plus nitrogen gives us lithium nitride. Well, first thing is on this one, all of the correct chemical formulas are already given, so that makes this particular type pretty easy. However, we'll find that that sometimes we're given problems like we will be in this next little section where we have to come up with the correct chemical formulas, and that is an important distinction. But here we're given the correct chemical formulas. Our second step is to look, is it balanced? Well, here we've got 1 lithium and 3 lithium, so no, that one's not balanced. 2 nitrogens and 1 nitrogen, so that is not balanced either. So the way that we're going to do this is we'll balance one element at a time, and we can either pick lithium or nitrogen. I'm going to pick nitrogen just because nitrogen's bigger. Nitrogen has an atomic number of 7, while lithium has an atomic number of 3, so nitrogen's bigger. All right, so with nitrogen, I have 2 here and 1 there, so I'm going to lock those 2 in place by putting a 1 in front of N2, and then we'll put a 2 here to balance the nitrogen. So now nitrogen is balanced. Next, let's balance the lithium. Well, here we've got 2 times 3, so 6 lithiums. So we'll simply come over here and put a 6 in front of lithium there. Now, that one's pretty easy, and if you had a whole test full of those, well, you would be doing really, really well in this class. So just a word of warning, you won't get a whole test full of those ones that are that easy. All right, so next we've got ammonium nitrate, and that gives us nitrogen plus oxygen and water. And this is the decomposition of ammonium nitrate. So that is an important reaction. All right, so here we've got the correct chemical formulas. That's step 1. Step 2, is the equation balanced? We'll check. So we've got 2 nitrogens here, 2 nitrogens there. Well, that's balanced. Let's see, 4 hydrogens, 2 hydrogens. That's not balanced. 3 oxygens, 3 oxygens there. So the oxygens are balanced. It's just the hydrogen that isn't balanced. And when you look at that, you say, well, I can just balance the hydrogen and then I'm done. Not quite. Not quite. I'm still going to recommend you do exactly what I was talking about earlier, which is balance one element at a time, ones that are in one compound on each side, and start with the bigger of those first. So oxygen's in 2 things, so we're not going to do it until the end. For nitrogen and hydrogen, well, nitrogen's bigger, so we'll do nitrogen first. So here we've got 2 nitrogens, so let's lock those in place by putting a 1. All right, we'll lock those in place by putting a 1. Now for hydrogen, well, hydrogen, we've got, let's see, 4 hydrogens here. There's only 2 on the right side, so we'll put a 2 in front of H2O to give us 4 hydrogens there. Now for oxygen, we've got 3 oxygens on the left And over here, we've got 2 oxygens that are locked in place. So we only need 1 more oxygen out of this. And the way that we can get 1 more oxygen out of this is to put a 1/2 in front of O2. And that will give us the correct number of oxygens. Well, now we've got a fraction here. We'll go ahead and multiply everything through by 2 to get rid of the fraction. So we'll multiply 1 by 2 to give us 2, 1 by 2 to give us 2, 1/2 by 2 to give us 1, and 2 by 2 to give us 4. All right. Now, it's important to go through and double check to make sure that you get the right answer. So 2 times 2, there are 4 nitrogen. So nitrogen, 2 times 2, there's 4 nitrogen. Nitrogen's balanced. For hydrogen, 2 times 4 is 8. 4 times 2 is 8. So hydrogen's balanced. For oxygen, 2 times 3 is 6. 1 times 2 is 2. 4 times 1 is 4. 2 plus 4 is 6. So oxygen is balanced there. All right, well, now that we've done that, let's do the next one. For the next one, we've got calcium hydroxide plus phosphoric acid gives us calcium phosphate plus water. Now, there's a lot of things to choose here. And so we could pick, let's see, we can't pick hydrogen because hydrogen is in 3 different things here. Oxygen is in everything. So oxygen we're going to save till the end. We could pick calcium, let's see, calcium or phosphorus. So calcium or phosphorus. And when I look at my periodic table here, I'll see that calcium has an atomic number of 20 and phosphorus, here, I'm going to show you this. So calcium is an atomic number of 20, phosphorus is an atomic number of 15. So we're going to pick calcium first. All right, so calcium, we've got 1 here, 3 there. We'll lock those 3 in place by putting a 1 in front of calcium phosphate, and then we'll put a 3 here for the calcium. All right, so calcium is now balanced. Now let's look at phosphorus. Well, phosphorus, we've got 2 of the phosphate, so there's 2 phosphorus atoms. So 2 there, and here we only have 1, so we're going to put a 2 in front of the phosphoric acid. So next, we could either pick hydrogen or oxygen, and it turns out the hydrogen is a little bit easier here because this doesn't contain hydrogen, so this is the only thing that has hydrogen in it. So let's count up the oxygens. 3 times 2 times 1, that's 6. 2 times 4 is 8. 6 plus 4 is, 6 plus 8 is equal to 14. So 6 plus 8 is 14. Oh, all right. And I just said we were going to do hydrogen. Let's do hydrogens. All right, 3 times 2 times 1 is 6. 2 times 3 is 6. 6 plus 6 is 12. To get 12 out of this, we'll put a 6 in front of water. All right, I said, oh, we're gonna do hydrogen. We're not gonna do oxygen. We'll do hydrogen, and then I started counting the oxygen. So it just shows old habits die hard. All right, at this point, it's a really good idea to double check. And again, I just like going from left to right. So I'm gonna start with calcium. 3 calciums. 1 times 3 is 3 calciums. So calcium's good. For oxygen, 3 times 2 times 1 is 6. 2 times 4 is 8, and of course 6 plus 8 is 14. And then over here, 1 times 2 times 4 is 8, plus 6 more, that's also 14. So oxygen's good. Hydrogen, we just did this one, but we'll double check it again. 3 times 2 times 1 is 6, 2 times 3 is 6, and then 6 times 2, so 6 plus 6 is 12, and 6 times 2 is also 12. So we're good there. And then finally, phosphorus. That's the only one we haven't done yet. 2 times 1 is 2, and then 1 times 2 times 1 is 2. So that is a balanced chemical equation. All right, next we've got silver nitrate plus sodium sulfate gives us silver sulfate plus sodium nitrate. And you'll see oxygens in everything. So we should save oxygen for the end. We could pick silver because it's in one thing on each side. We could pick nitrogen because it's in one thing on each side. Sulfur is in one thing on each side. And sodium is in one thing on each side. All right. Of those, the biggest atomic number is for silver. So I'm going to pick silver. We've got 1 here, 2 there. Let's put a 1 to lock those 2 silver atoms in place. And we'll put a 2 in front of this one. So our next biggest element is here is sulfur, I believe. Yes, so sulfur. Sometimes people get tempted to do the sodium, and in this case, it will give you the correct answer, but you want to build off something where you've already locked it in place. So you don't want to say, oh, here I've got 2 blanks, I'm going to just put the sodium in. Again, in this case, it's going to give you the correct answer, but that's a dangerous road to walk down. So always build off something where you've locked it in place. So one sulfur here and 1 sulfur there, so we'll lock that sulfur in place. Now let's go ahead and do sodium. Sodium, we've got 2 atoms of sodium, and we will put a 2 in front of sodium nitrate, and that balances the sodium. You'll notice that we have not even looked at nitrogen or oxygen. So we definitely want to go through and double check our work. So we'll just go from left to right. We'll start with silver. 2 times 1 is 2. 1 times 2 is 2. So silver is good. Sometimes you may even want to go over and have a little checklist and make sure you've done everything. So silver is good. For nitrogen, 2 times 1 is 2. And then over here, 2 times 1 is also 2. So nitrogen's good. Oxygen, this is the one that we really need to check. So 2 times 3 is 6. 1 times 4 is 4. 6 plus 4 is 10. Here we've got 1 times 4, that's 4, and 2 times 3 is 6. That's also 10. So 10 oxygens is good. For sodium, 1 times 2 is 2, and then 2 times 1 is also 2. So now sodium is balanced. Let's look at sulfur. 1 and 1, so sulfur, and then we've already done oxygen. So this one is balanced. All right. Finally, let's look at E here. So on this one, we've got, this one is the combustion. We've got methylamine plus oxygen gives us carbon dioxide plus water plus nitrogen gas. All right. So now what we want to do is we want to look, is it already balanced? And the answer to that is no. Carbon is balanced, but you'll see nitrogen isn't. We've got 1 and 2. Hydrogen, we've got, let's see, 2, we've got 5 there and only 2 here. So this is not a balanced equation. So we're going to start with, we could pick either carbon or nitrogen or hydrogen. And of those, the biggest one is nitrogen. So I'm going to pick nitrogen. So I've got 1 nitrogen here, 2 there. So we'll lock those 2 in place by putting a 1 in front of N2, and we'll put a 2 here. Our next biggest element is carbon. So we'll do, we've got 2 carbons here. So we'll put a 2 in front of carbon dioxide. And now let's look at the hydrogens. Hydrogens, we've got 2 times 5, and pay attention that we've got 3 plus 2, so 5 hydrogens in each of those molecules. So 2 times 5 is 10, and to get 10 hydrogens here, we're going to put 5 times 2, and that will give us the 10 hydrogens. Now we need to check the number of oxygens. So we have oxygen here. We can put whatever number we need to balance it. 2 times 2 is 4, plus 5 more gives us 9. And so 9, we're going to use 9 halves to make that work. And just like what we did before, for step 5, where it says multiply the coefficients, if you go back to this, you'll see step 5, multiply the coefficients if necessary to eliminate fractions. Well, we're going to eliminate this fraction by multiplying everything through by 2. So 2 times 2 is 4. 2 times 9 halves is 9. 2 times 2 is 4. 2 times 5 is 10. And 2 times 1 is 2. All right, now that we've done that, we should double check to make sure everything works. And we have quite a few atoms here, so it's definitely worthwhile to check this. All right, so 5 times 4, that's 20, and 10 times 2, that's 20. So that's 20 hydrogens. For carbon, 4 times 1 is 4. 4 times 1 is 4, so we've taken care of carbon and hydrogen. Nitrogen, 4 times 1 is 4. 2 times 2 is 4, so nitrogen is balanced. So we've taken care of carbon, hydrogen, nitrogen. Oxygen, 9 times 2, that's 18. Here we've got 4 times 2, that's 8. 10 times 1, that's 10, and then none there, so 8 plus 10 is 18. So that is balanced as well. So you can do any of these. I want you to get good at this. This is an important skill, and if you have trouble with it, you are going to have trouble with a lot of other things. Okay, so we'll switch back over to our presentation, and we're going to talk about reaction types. And the first reaction type that we're going to discuss is combination reactions. Combination reactions, this is where we take 2 or more chemicals and they combine together to make one chemical, one product. And I've got several examples here, and the several examples are let's see, nitrogen plus hydrogen gives us ammonia. This is actually a very important industrial process, is producing ammonia. And then here, this is one I do with my organic chemistry students. So C3H6 plus Br2 gives us C3H6Br2. So you'll see we went from 2 things on the left to 1 thing on the right. And then here we've got 2 magnesiums plus an oxygen molecule gives us 2 MgO. So again, we've got 2 reactants and 1 product. All right, that is an oxidation. For the on-campus class, this is one that we do in lab, and where we actually take magnesium. We don't burn it in the open like this because the smoke that comes off is actually some of our product, and we want to isolate the product. But when we heat it up, and we do this in a crucible, we heat it up and we will produce magnesium oxide. It's a pretty cool little experiment, but this is a combination reaction, and I've got several other combination reactions I want to show you on this video that's combining elements with oxygen. And here we go. So I'm going to click on this and you guys can watch this video.
Burning magnesium ribbon burns even more brightly in oxygen, producing a white smoke of solid particles of magnesium oxide. Let's watch that again. Burning steel wool burns vigorously in oxygen, giving a shower of sparks and brown solid iron oxide, Fe2O3. When a small piece of white phosphorus is placed in oxygen, it ignites spontaneously and burns with a very bright flame, forming a dense white smoke of solid oxide, P4O10. Here is the oxide at the bottom of the jar. If sulfur is heated in a Bunsen flame until it melts, it will burn in air. When it begins to burn, we plunge it into oxygen gas, where it burns even more brightly. In oxygen, it burns with a bright blue flame, producing the pungent-smelling gas, sulfur dioxide.
All right, so that is a series of reactions that where we combine elements with oxygen to produce their oxides. Kind of a cool set of reactions there. All right, so that's combination reactions. Our next type of reaction that we want to look at is a decomposition reaction. And decomposition reactions are kind of the opposite of combination reaction. Here we have one substance that breaks apart into 2 or more substances, and it usually happens after heating a substance. So here are a couple of examples of this reaction. The first example is calcium carbonate. That is the primary ingredient in chalk. So if you take calcium carbonate and heat it up to a really high temperature, you'll get calcium oxide and carbon dioxide. So you'll see one substance gets converted into 2 substances. Here we have potassium chlorate. Potassium chlorate will decompose to give us potassium chloride plus oxygen. We used to do, we used to do the potassium chlorate reaction in lab, but it turns out that one, it was just a little too dangerous to do that one, so we've stopped doing that one just because the risk of injury was a bit too high. Here's another one. This one also is not something we would do in the lab because when it decomposes explosively. Very exciting. And that is sodium azide. And if you heat up sodium azide, you'll get sodium metal plus nitrogen gas. And that nitrogen gas is hot and it expands really quickly. So that is, like I said, a very exciting reaction, not one where you want to be right next to it, unless of course it happens to be in an airbag. And this is a little drawing of an airbag. And what happens is that there is a little switch, and when your car comes to a very quick stop, in other words, it runs into something, it causes that switch to flip. And when it flips that switch, it ignites your sodium azide, so it heats it up in a little heating element, heats it up very quickly. And over the course of just about 50 milliseconds, it completely decomposes and fills the airbag with hot nitrogen gas. And so that is how the airbags work. And I actually have a little video that comes from the publisher. And so I'm going to go over and we are going to watch this.
An airbag is a rapidly inflating cushion that helps to prevent auto crash injuries. When there is a sudden deceleration of the auto, a switch is thrown which triggers the start of a chemical reaction that produces a gas. The chemical reaction employed is the thermal decomposition of sodium azide, NaN3. Upon heating, sodium azide decomposes rapidly to form sodium metal and nitrogen gas. The reaction is exothermic and rapid once it has begun. In practice, an oxidant is added to react with the sodium to form sodium oxide. When the reaction is triggered by a sudden application of heat, the hot nitrogen gas formed by decomposition of the sodium azide expands into the airbag. Expansion occurs in only about 50 milliseconds. After the initial expansion, the hot nitrogen gas cools and the bag partially deflates, freeing the passenger. Notice that no new substance has been introduced into this closed system during reaction. The large volume difference between reactants and products is due to the fact that one of the products is a gas.
All right, so that is an example of a decomposition reaction, a useful example. If you've ever been in an accident where an airbag was deployed, and if that's happened to you, sorry about that. That is not a very pleasant experience. But if you've been in an accident where an airbag has been deployed, you will notice, one, that the airbag will be quite hot. And it's not unusual for people who are in accidents, in addition to bruises and stuff, that they sometimes have burns on their legs or hands or sometimes face because of the hot gases. They're not major burns, and they're better than the consequence of like running into the dashboard or the windshield, but sometimes they can be very unpleasant. So an airbag going off is not something you want to experience unless you have to, of course. So, okay, so that is decomposition. So we've looked at combination and decomposition, and now we want to look at combustion. So for combustion reactions, and so here we've got the combustion reactions. These are rapid reactions that produce a flame. Typically, they'll involve hydrocarbons reacting with oxygen and air. You'll have a hydrocarbon when it burns, it will produce carbon dioxide and water. We saw a video of this earlier, so I'm not going to show another video. This one is the methane that burns to give us carbon dioxide and water vapor. But another one is propane, and here is a picture of a propane torch. When you burn propane, it will produce carbon dioxide and water. So we're going to look at several word problems. So 3.18. We're going to look at several word problems that have that are balancing equations, but we have to come up with the correct chemical formulas, and that is an important concept. So we're going to switch back over to the in-class assignment. And here in our in-class assignment, we'll start with this one. Aluminum metal undergoes a combination reaction with Cl2. Well, of course, aluminum metal is Al solid. I'll put that in parentheses there. And I am going to put a little space out front, kind of like I did on these previous ones, so that we can balance them. And then chlorine is Cl2 gas. All right. And this is one of those examples where it's really important to come up with the correct chemical formula. So when we have a combination between aluminum and chlorine, we're going to make aluminum chloride. Well, as you remember, aluminum is in group 3, so aluminum forms a +3 charge. Chloride is -1, so +3 and -1, we're going to have AlCl3. So our product is AlCl3. And it turns out that that's an ionic compound that ends up being a solid. All right. It turns out when I give this problem to students, one of the common mistakes is they see Al and Cl2 and they'll write AlCl2. Well, that would be the wrong thing to do. And the reason it would be wrong is because that compound just doesn't form. So you have to come up with the correct chemical formula and then balance it. All right, so let's balance this. None of the things are balanced, or aluminum is, but the chlorine isn't. So let's do this. Let's balance the chlorine, and I can already tell this one's 2 and this one's 3. If I do the least common multiple of 2 and 3, that gives us 6. So that means if I put a 2 in front of this, all right, that gives me 6 chlorines there and a 3 here. Now chlorine is balanced, and I won't get any fractions this way. All right, and now we have two aluminum, so I'll put a 2 out front, and that is a balanced equation for aluminum plus chlorine to give us aluminum chloride. Next, we've got copper 2 hydroxide. Well, copper 2 is Cu2 plus. Hydroxide is OH minus. There's copper 2 again. Oxide is 2 minus, O2 minus. And then, of course, water vapor. I don't need to write that one out. So we're going to start with copper 2 hydroxide. So CuOH2, because the 2 there, that has to balance. That is an ionic compound, so that is a solid. And it will decompose to form copper 2 oxide. Well, if we have copper 2 and oxide is -2, then we're going to get CuO, solid. And then water vapor, we'll put H2O. And since it does say vapor, we'll put gas. Sometimes the reaction will indicate vapor. Sometimes it'll indicate liquid. So you'll have to be careful when you are figuring those out. All right, so now let's look at this. We've got copper. Let's check and see if it's balanced. We got one copper, that's good. We've got 2 oxygens, 2 oxygens, that's good. 2 hydrogens, 2 hydrogens. This is the rare case where everything is already balanced. So all the coefficients here are 1. Now, of course, when you have coefficients of 1, you don't necessarily have to write them. But since we put the spaces in there, I'm going to go ahead and put the 1s in. But if you were just writing this out and weren't putting the spaces in, then you could just write it without those coefficients. All right, our next one is combustion. So we've got MTBE, so C5H12O liquid. I'll go ahead and write that one. C5H12O liquid. It burns in air. Well, air, the thing that it burns in, of course, is oxygen gas. So this is a combustion reaction. The products of a combustion reaction are just like what we saw a minute ago. When we do the products of a combustion reaction, we're going to get carbon dioxide gas and H2O. All right, and it didn't specify whether it is liquid or gas. If it doesn't specify, I usually will put gas. But if you're working problems in mastering chemistry and you've got everything balanced and it says check your states, sometimes water they look for it as a liquid. So just kind of be aware of that. All right, so now that we've done this, let's check and see if it is balanced. It's not balanced, right? We've got 5 carbons here, only 1 there, 12 hydrogens, only 2 there, and then oxygens, it's the same number of oxygens, but that doesn't matter because the rest of it is not balanced. So let's start with carbon. And typically when you're doing combustion reactions, carbon will be the first thing you balance unless there's something else in there like a chlorine or a nitrogen or something like that. So we're going to start with the carbon. We've got 5 carbons here. I'm going to put a 1 in front of that because 5 carbons, and we'll put a 5 in front of carbon dioxide. For hydrogen, so for hydrogen, we've got 12 hydrogens here. To get 12 out of this, we're going to put a 6 in front of the H2O. Now let's balance the oxygen. So 5 times 2 is 10. 6 times 1 is 6. 10 plus 6 is 16. We need 16 oxygens here, but you'll notice that we've already got 1 of those oxygens in place. So we only need 15 oxygens out of this. So we're going to put 15 halves in front of that O2. So now that we've done that, let's go ahead and multiply this through and get rid of the fractions. We'll multiply everything through by 2. So we'll get a 2 there, a 15 here, 10 there, and 12 there. Definitely, you want to double check your work to make sure that that everything is balanced. So we'll do 2 times 5 is 10. 10 times 1 is 10. So 10 carbons. We're good with carbon. Hydrogen, 2 times 12 is 24. 12 times 2, also 24. So hydrogen is balanced. Oxygen, 2 times 1 is 2. 15 times 2 is 30. 2 plus 30 is 32. 10 times 2 is 20, plus 12 more is also 32. So we've got a balanced chemical equation here. All right. So practice, practice, practice. You want to get really good at balancing chemical equations. All right, we are at, 47 minutes. So I'm going to stop this video and I will pick up with the next section on video number 2.